So in your previous class we learned about carbons as one of the key intermediate. Later on we also introduced nitrine as an intermediate. So carbon chemical reactions we learn. In the same way we also learn general introduction of a nitrine. So how nitrines show singlet character as well as triplet character. So now today we are going to discuss about chemical preparations as well as chemical properties and trapping methods of nitrine. Okay. Now see, preparations or generations of nitrines. How to generate a nitrine? Generations of nitrine. Yes, see, nitrines are get generated by using a following molecule. See, this is hydroxamic acid derivative. This is S double bond O, S double bond O, Ar. Hydroxamic acid derivative. So this is on treatment with a base and thermal heating. Then what happens? See, first it will undergo deprotonation. After deprotonation you will get an anion. So here there is a formation of this derivative and this is undergo elimination under thermal condition, and finally see there is a formation of a nitrine. Okay, nitrine forms by taking a hydroxamic acid derivative. Hydroxylamine. What is NH2OH? Hydroxylamine. This is called hydroxylamine derivative. This is undergo basic treatment. This base will take this proton and these electrons will be migrate here, and thermally they will decompose and form say nitrine. So nitrines are monovalent nitrogen intermediates. Now see, I am taking a alkyl azide. This is called RN3. This RN3 you can write like this: nitrogen nitrogen triple bond, and this is plus and this is minus. This is called alkyl azide. When alkyl azide on thermolysis or photolysis, alkyl azides on thermolysis or photolysis, there is a loss of N2, and finally see there is a formation of nitrine. Nitrine is a monovalent nitrogen intermediate. Okay, and we can also take acyl azide. What is this? Alkyl azide. Now it is acyl azide. In place of this alkyl, now I am replacing with a acyl group. So this you can also write like this: RC double bond O, nitrogen carry, triple bond. This is plus and this is minus. It is also thermal or photochemically removed out. So remove this N2, finally see there is a formation of a acyl nitrine. Every time nitrogen carry 4 electrons. What is this? Acyl azide. What is this? Alkyl azide. What is this? Hydroxylamine derivative. Okay, sulfonyl derivative of hydroxylamine. So they treat with a base followed by thermal decomposition. There is a formation of a nitrine. Alkyl azide on thermal or photochemically, if you irradiate, that will give nitrine. This is called acyl azide. One name reaction is there, Curtius. Okay. So what is this? This is called acyl azide. And what is this? This is called alkyl azide. Now I am taking hydrozoic acid. What is an HN3? Hydrozoic acid. Hydrozoic acid, otherwise we can take ammonia, otherwise we can take N2H4. What is N2H4? Hydrazine. N2H4 is hydrazine. This is on treatment with electric discharge. See, if you want to prepare a nitrine which carry only hydrogen on nitrogen, so directly photolysis is not a suitable method. Only with electric discharge there is a possibility of preparing nitrogen carry 1 hydrogen. Only electric discharge method have a tendency to prepare a nitrine which carry hydrogen. Okay, right. Hydroxylamine derivative. This is called alpha elimination. Alpha elimination means from one nitrogen we are removing hydrogen as well as this bond. So finally you will get nitrine. Names are very important. Hydroxamic acid derivative or hydroxylamine derivative. Electric discharge responsible to give nitrine which carry hydrogen. So in this method is not possible. Alkyl azides, if you make a direct photolysis, you will get only alkyl nitrine only. If you want to get a nitrine which carry hydrogen, only electric discharge is the best method. This molecule name is very, very important. It is helps in courteous rearrangement. Acyl azide, acyl azide, alkyl azide. If I write one hydrogen, that is called hydrozoic acid. This is called hydrozoic acid, HN3, hydrozoic acid. Ammonia, hydrogen, these all are responsible to give nitrine bearing hydrogen. Next, C. When alkyl attaches to nitrogen and this is C double bond O. What is this? This is called isocyanate. Isocyanate, not isocyanide, isocyanate. Isocyanate on photochemical or thermal decomposition, so it will be breaks like this and there is a formation of a nitrine. And what is removed here? Carbon monoxide. This point you remember. When nitrines reacts with carbon monoxide forms isocyanate. Back reaction is also possible. Nitrines are highly sensitive nitrines combine with carbon monoxide from atmosphere and get converted to isocyanate. This is DL question. Reverse they given. What happens when nitrine combine with carbon monoxide? Nitrine combine with carbon monoxide, below they given names. Okay, they given carbon dioxide, ammonia, hydroxylamine, one more is isocyanide, isocyanate. Okay, now answer is isocyanate. Next, and if carbon is replaced by sulfur, this is called sulfonyl amine. Sulfonyl amine. When this is upon thermal or photochemical decomposition, what happens? See, here also see there is a formation of nitrine and loss of sulfur monoxide. Sulfonyl amine. Sulfonyl amine also responsible to give nitrine. This is AR, S double bond O. Next here nitrogen carry H. This is C double bond OET. C double bond OET. Okay. Now here also on treatment with base and thermal decomposition. So this is called N. This nitrogen carry N aryl. Okay. So this is called sulfur noate. Sulfonoate carbamate. Sulfonoate carbamate. Otherwise you can say sulfonoxy. Even you can also say sulfonoxy. This is called sulfonyl and this is also called sulfonoxy. So N-aryl sulfonoxy. Ester derivative you can also say sulfonoxy. Sulfonoxy carbamate. So N-aryl sulfonoxy carbamate. This is carbamate skeleton. On thermal decomposition, what happens? See, there is a formation of a nitrine. So this will be removed out and this ester part will be as it is. Sulfonoxy. That's why we can also write O8. Sulfonoxy. You can also write sulfonoxy. O8 indicates this one. Suppose if you want to write O8, carbonate is a carbamate, not carbonate. Carbamate is a primary skeleton. Sulfonylamine, aryl sulfonoxy carbamate. SULFONOXY. Okay, and this is most important one. When you reacts with nitroalkane, otherwise nitrosyl derivative or NO on treatment with triethoxyphosphate. Triethoxyphosphate. Now this source is responsible to give nitrine. Nitroalkane, otherwise nitrosyl. Alkyl nitrosyl derivative also responsible to give nitrine. This is important reaction. Remember, when nitroalkane is given, that nitroalkane on treatment with triethoxyphosphate. Triethoxyphosphate, that will give nitrine. Remove oxidants and you will get this answer. And this is the question which is given in exam. Here see double bond and I am writing pH and this is CH3 double bond and they given NO2. This is CSR question. If this molecule is given and they will give like this, triethoxyphosphate. Now what is the answer? Now this becomes a nitrine or not? This NO2 nitro becomes nitrine. So after conversion of nitrine, now this is CH3 and this is pH. Now this becomes a nitrine like this. Nitrine having empty orbital, this will attack on this empty orbital. Now nitrogen becomes a anion. So after converting into anion, now what is the charge you will expect on this one? Positive charge or not? This is positive charge. Now what about here? Here pH and methyl both are present. Now phenyl migrates from here to here. Now that becomes unstable. So after instability, what happens? Now this nitrogen adjacent, there is a carbocation formation takes place. Now phenyl migrates here. Now why you are migrating phenyl? Why not methyl? So we need to create an unstable carbocation so that it can attract this negative charge. Okay. Now this negative charge is get attracted by this unstable cation. After attraction, what happens? There is a formation of carbon nitrogen double bond, and this methyl is as usual and here phenyl is as usual. Now this is undergo tautomerism. Once if they undergo tautomerism, what is your final answer? Final answer is indole or not? So here see, this is indole, double bond, and this is pH and this is CH3 and here hydrogen. Indole is your final answer. Indole preparation. So when this molecule is given, put a bond between these two. So whichever group will create more stability regarding carbocation, that group you need to migrate over here, and finally cation stabilized by negative charge and you will get double bond. Now you will get enamine. Enamine upon tautomerism gives finally imines. This is imine, carbon nitrogen, when this combine together you will get imine, right? Imine upon tautomerism gives enamine. So enamine is now, it is involved in aromaticity. So now this is a stable molecule in this one. This you take down as a question. This may help in chapters, individual chapter while you are learning. Intermediate has been generated. After generation of intermediate, how to trap that intermediate and what are the expected chemical reactions for that intermediate. This I am writing here. So what is the structure of indole? Is it 5-membered or 6-membered? 5-membered. Here I am writing methyl and here I am writing phenyl. So what is EPS position in indole? EPS position in indole? Third position. Nucleophilic, see this position we need to substitute a electrophile. Wheels-May-Reck reaction, Riemann-Timmins reaction, alkylation, acylation, nitration, etc. Every heterocycle, whenever if it is appeared, try to recollect EPS and NPS positions, alkylation, etc. So which is active hydrogen? Where active hydrogen present in indole? Third carbon. Clear? So that is preparations of or generations of nitrine. Nitrines can be prepared by alpha elimination of hydroxylamine derivative. Alkyl acids on photolysis, thermolysis will give nitrine. Acyl acids also, thermolysis, photolysis may give nitrine. In the same way, if you want to prepare a nitrine which not having any alkyl group or nitrogen or only hydrogen you want to prepare, then straightforwardly electric discharge is the best method to prepare nitrine. Later on we learn how to make a preparation by using isocyanate, then sulfonylamine, then sulfonoxy derivative. So sulfonoxy carbamate, and finally by using a nitro derivative. Okay. Next. Now stability. This stability almost all equal to carbene only. Carbene stability and this stability almost all same. Is it electron deficient or not? Nitrine is electron deficient. Electron releasing groups increases. Stability or not? Stability of nitrine. Electron releasing groups increases, stability of nitrine. It is similar as that of normal part. See, this is a nitrine having only methyl group. Now I am writing a ethyl group. Next I am writing isopropyl nitrine. Next tertiary butyl group attaches to nitrine. Which is more stable? Which is more stable? Fourth one is more stable as compared to third one, second one and first one. Plus inductive groups, plus mesomeric groups are effectively stabilized nitrine. Why? Because they carry empty p orbital. Okay. Now here conjugation is present on nitrogen. Now there is no conjugation, directly nitrine I am given. Okay. So which is more stable among these two? Suppose if I give continuous conjugation on nitrine, which is more stable? Third one is more stable than first one and then followed by second one. Nitrine stability. As conjugation increases, stability increases, nitrine. Okay. Now see, when mesomeric group is attaches to nitrogen, see this is mesomeric group having a lone pair of electron, here empty p orbital is present. Next CH3 attaches to nitrogen. CH3 attaches to nitrogen. Then carbon-carbon double bond attaches to nitrogen. So which is more stable? Which is more stable? Now plus mesomeric effect, it will stabilize by releasing electron. First one is more stable than third one, then second one. Here mesomeric stability, here conjugate stability, now here inductive stability. So even you can apply mesomeric effect, inductive effect, especially in case of nitrines. Clear? Next. Here it is detection. Detection methods or identification methods of nitrine. So very easy. Nitrine is get trapped in the form of azirine as well as aziridine, etc. Suppose if nitrine is an intermediate, now I want to add a olefin. When olefin is added to nitrine, C, then what happens? It is get trapped in the form of, it is similar to carbon or not? Now nitrogen is get trapped here, cycloaddition. This will migrate here, this will add here now. What is this? Irine, iridine, aziridine. This is aziridine. Now if I add a triple bond, when carbon-carbon triple bond is added to nitrogen, now here, this will combine here, this will migrate out, and finally see, can I get a double bond or not? Carbon-carbon double bond, and here nitrogen will be like this. So this is R. What is this? Azirine. So many examples are there. We can write by using a carbon monoxide. See, here formaldehyde is present. This is formaldehyde. Is it formaldehyde or not? Or carbon monoxide? Formaldehyde. So when formaldehyde combined with nitrine, then what is the answer? Now carbon connected to oxygen and nitrogen. Now see, this is carry R and two hydrogens. What is this? Oxaziridine. All heterocyclic compounds are going to be affected in this one. So what is the final trapping method? You will get a cyclic ring, in that nitrogen is going to be introduced. So before we are adding a molecule of unsaturation which don't carry nitrogen, finally you are getting a nitrogen, which means it is a nitrine intermediate. Is it similar trapping method of carbon or not? Same. So that are the trapping methods of nitrine. Next, chemical reactions of nitrine. What are the available chemical reactions of nitrine? Nitrine chemical reactions almost all analogous to which one? It is approximately equal to carbene only. Chemical reactions of nitrine. Now first one, this is already given. What is it? Cycloaddition. What happens cycloaddition of olefins and carbene? Suppose see if I take a carbene, what happens when I introduce a singlet carbene to olefin? Singlet carbene to olefin. So it is a concerted and stereospecific or not? Right now I am taking a nitrine which is a singlet. Suppose see here I am using a lone pair and here also lone pair. Now what happens, is it singlet or not? Now whenever if I take a singlet nitrine, now these two electrons combine together back to back and see you may get only one product. Will you get one product or mixture of two? Only one. So can I say singlet nitrine is it concerted or not? Concerted, and what is one more? This is stereospecific. When singlet nitrine is added around olefin, that will give always only one product. Suppose if I take a trans, then addition of singlet nitrine, you will get a trans isomer. Right now see I am taking same olefin, but see here nitrogen having lone pair, here opposite spin is there. So then what kind of nitrine it is? Is it triplet or not? When triplet nitrine is given, now see mixture of two products are expected. Now you will get cis, this is one product, and here one more trans, you will get one more product. So which is major in this one? Trans is major. So is it concerted? No, it is non-concerted, non-stereospecific. So it is no need to learn separately. Why? Because already in carbene we learn, so you can take directly now. Okay. So when olefins added to singlet nitrine, that will give concerted stereospecific product. Cis to cis, trans to trans only. But whenever if you add any olefin around a triplet nitrine, you will expect a non-concerted and one more is non-stereospecific products are major. So out of cis and trans, trans is major as compared to cis in this reaction. Right. Non-concerted, below you write non-concerted, non-stereospecific. So it is a non-concerted, non-stereospecific. Now always write down trans is major as compared to cis. Next is insertion reactions. Nitrines also involved in insertion reactions. So what is insertion? Adding nitrine in between carbon and hydrogen bond. Insertion is different, abstraction is different. Abstraction nothing but it will take hydrogen first. Insertion nothing but we are inserting in between carbon and hydrogen bond. Suppose see if I take a Rn, 2 electrons are present here now. Now this carbon carry how many bonds? 4 bonds are present. Now this nitrogen is inserted between hydrogen and carbon. Okay, insertion, what is insertion? Insertion nothing but we are forcefully inserting. Small kids generally if you see small children they won't eat food. What we will do? We will insert. Here also same. So we are inserting. Abstraction is nothing but, what is abstraction? Some food is there, so from there onwards you are abstracting. Means attraction. If you are very hungry on that time what you will do? You will abstract. By inhaling that smell also you will abstract the complete food. Insertion is different, abstraction is different. Forcefully we are inserting this in between carbon and hydrogen. Okay. So on that time what is the answer? Now can I write like this? Here hydrogen, now here nitrogen. Nitrogen is bonded between these two. This is called insertion reaction. Okay. So break this bond, in between these two nitrogen will come. That is called insertion reaction. Now here what is the reactivity order in this insertion reaction? So here also remains same. Already I given benzyl is more reactive than allyl, then followed by tertiary, secondary and primary hydrogen. Primary carbon hydrogen is the reactivity order. This is most important for your exam. As come here in this one, only one point you remember. Singlet nitrine, singlet carbene addition is a concerted stereospecific, but triplet is a non-concerted, non-stereospecific. Insertion reactions are nothing but inserting nitrine or carbene between carbon and hydrogen. And if multiple carbon hydrogen bonds are present, give priority for benzyl, allyl, tertiary, secondary and primary. Suppose if I take like this, nitrogen, here carbon, hydrogen, same kind of question I will give. Two possibilities are expected in this one, carbon, hydrogen, carbon, hydrogen. So what is the answer? How many insertions are expected here? How many different types of insertions are possible? Now nitrine, 2 electrons are present, here also 2 electrons. Can I break here? Break, insert nitrogen between these two. And one more, between carbon, hydrogen also possible or not? How many products will expect? 2 products or not? So what is the major product here? This is carbon, hydrogen. Can I put like this, nitrogen R and here hydrogen? Can I write like this? Is it major? It is major. So what about minor? How to write minor? This is CH, CS3 and here this is CH, CS3 like this. And here one more, CS3 I am writing now. Here one of the hydrogen I removed, I am introducing this one. Here hydrogen and what is one more? That is R. So this is minor and what about this? It is found to be major. Insertion of nitrines always leads to form amines. Insertion of nitrine leads to form amine. Clear? Next is dimerization reaction. Nitrines also involved in dimerization. The generated nitrine also have a tendency to form a dimer. Suppose see, if I take a nitrine having bonds like this is nitrine. Nitrine on dimerization. So this will give diimides. This is one in situ reagent, diimide, N2H2. What is this? This is called diimide. Diimide. Suppose if I take a methyl nitrine, methyl attaches to nitrine. Now 2 equivalents of same nitrines will combine together now. So what you will expect? Methyl is attaches to nitrogen, nitrogen double bond, and see this is the one. So azomethane. What is this? Azomethane formation takes place. Okay? And see, if I take aryl, aryl on dimerization. So in your examination they may give like this. Aryl on dimerization will give. So aryl ring is that attaches to nitrogen, nitrogen, double bond, and finally air. Okay? So this is dimerization reaction, and one more you can also expect disproportionation. What is disproportionation? Oxidation and reduction. Oxidation reduction is known as disproportionation. So self oxidation, self reduction is called disproportionation, redox reaction. Okay? See, if I take a nitrine, nitrine undergo oxidation and reduction, then what happens? See, this will give N2 as well as H2. This is called disproportionation reaction. Nitrine 2 equivalents of nitrine will give N2 as well as hydrogen gas. This is called disproportionation. One name reaction is there which undergo disproportionation, Cannizzaro. Cannizzaro reaction is a disproportionation reaction. Right. So cycloaddition, insertion, one more is dimerization, at last disproportionation reactions, which are common reactions for nitrine. So what is the valency of nitrine? Valency of nitrine. Here how many bonds are written? One bond, one only. What is disproportionation? Self-oxidation, self-reduction. Clear? Now, see, you can also expect some rearrangement reactions with this one. Rearrangements. Some rearrangement reactions also possible with nitrine. So first one is Hofmann rearrangement. Only I will show the mechanism which will responsible to identify a nitrine. Our target is to identify nitrine in that one. That's why I will give directly nitrine reaction. Hofmann bromamide, Hofmann chloramide rearrangement reaction separately we will learn, but right now we will give only mechanism. So what is Hofmann rearrangement? See, RC double bond O and this is NH and here NH. What is this? Primary amide. What is this? Primary amide. When primary amide on treatment with bromine in sodium hydroxide. See, first what happens, see, this nitrogen is taken by this base. After taking this base, what happens, see, you will get a anion, N amino anion. So otherwise you can say anion of amide. It is anion of amide. Now this is combined with a bromine molecule. Now it will attack here, one of the bromine atom is removed. Now this nitrogen carry hydrogen and one more bromine. Can I write like this? This is called N-halo amide derivative. Okay. Next here one more equivalent of sodium hydroxide will take this proton. After taking proton, what happens? Here this nitrogen carry negative and this is bromine. Now what is this? N-halo amide anion. This is very, very important one. N-halo amide anion. This is intermediate in this reaction. N-halo amide anion. This is called primary amide. When nitrogen carry two hydrogens, this is called primary amide. In Hofmann rearrangement, definitely nitrogen should carry definitely two hydrogens. Suppose if this nitrogen carry only one hydrogen or no hydrogen, no reaction. Hofmann is not possible. Okay. Now after getting this amide anion, this nitrogen will migrate here. Now this alkyl migrates from here to here and this bromine is removed out. Okay. So after migrating, what is the answer? RNC double bond O like this. What is this? Isocyanate. Isocyanate on reacting with water molecule. Now see, this will attack here, back to back resonance will come and one more time it will come on nitrogen. And see, nitrogen carry one hydrogen and this is C double bond OH or not. Can I write like this? So after that, this is unstable under acidic medium and basic medium. Loss of carbon dioxide will takes place, CO2, and this hydrogen will be added here. So finally what happens? There is a formation of NH2, and what is removed here? Carbon dioxide. So what we are converted? Amide to. This is called primary amide. Primary amide we are converting into amine. Primary amide to amine. This is called Hoffman degradation reaction. So same kind of reaction you observed in case of untested. In untested we are introducing one carbon or not. But here see, this we are removing completely. So this group we are removing and we are putting a bond between these two. Right or not? That is called homologation, and this is called degradation. Degradation means loss of one carbon. Degradation nothing but loss of one carbon. So conversion of primary amide to primary amine is a chain degradation reaction. That's why this name is Hoffman degradation reaction. One more name is there, Hoffman degradation, Hoffman bromamide, Hoffman chloramide, etc. Okay. Now where carbons are observed here? Where nitrines are observed? Actually our concept is nitrines or not? Nitrines and carbons only. So in Hoffman untested rearrangement and Hoffman rearrangements, approximately some similarities will be there. So in case of untested, there is a intermediate Wolff rearrangement is observed. Same, loss of bromine, loss of N2, migration of R on nitrogen, on that case on carbon. Now see in this case, what you observed is R C double bond O, nitrogen carry which charge? Negative. This is Br. Now see, when bromine is removed here first, bromine is removed in terms of Br minus, and nitrogen is appeared in the form of nitrine. This is called acyl nitrine. After formation of acyl nitrine, this R migrates from here to here, this lone pair migrates like this. And finally what happens? R N C double bond O like this. What is this? Isocyanate. But here I given these two steps into one step only directly. Suppose if it is a multi-step reaction, same explanation as that of untested. Suppose if it is a multi-step reaction, when this molecule acyl nitrine on treatment with water, now what is the answer? You may expect nitrogen with hydrogen and one more hydroxy. Okay, N-hydroxyamide, hydroxamic acid. This is called hydroxamic acid. So there is a formation of hydroxamic acid. But whenever if you add water molecule, this is unable to trap. It is impossible to trap. We are not getting this one. Why? Because it is found to be unstable. Without this intermediate, this is impossible to prepare. Try to understand. Without this intermediate, it is impossible to prepare, but this intermediate is unable to trap. Right or not? So this molecule responsible to give isocyanate. See, is this nitrogen accepting this R minus or not? Okay, when this nitrogen accepting R minus means it is definitely a deficient species only. The deficient species is nothing but a acyl nitrine. This acyl nitrine is impossible to trap, unable to identify. Why? Because due to destability produced by acyl group. What is the role of acyl? It can withdraw electron. Already nitrines are unstable, then acyl group is withdrawing electrons, it is found to be unstable. So even if you add water molecule, due to its instability, they are unable to take this water. So hydroxamic acid formation is not exists. So finally we can say that it is a single step reaction. Loss of bromine is not a one step, migration of a group is not a another step. Loss of bromine, migration of alkyl takes place simultaneously. It is similar to untested Wolff rearrangement only. If you know untested Wolff rearrangement, no need to learn Hoffman. It is approximately same, but only thing is there you are getting a acyl carbon, right now you are getting acyl nitrine. Clear? Right. Take note. So these applications, and one more time this mechanism will be given in molecular rearrangement with intensive applications, but right now you focus only on this part. So we are converting primary amide to amine. So exactly reverse to untested or not. That is homologation. This is degradation. Their intermediate is carbon, now intermediate is nitrine. Their loss of N2, migration of R takes place simultaneously. Here loss of bromine, migration of R takes place simultaneously. There also intermediate is unable to trap, here also intermediate is unable to trap. Like that you need to compare so that you can remember very easily. If you know untested Wolff rearrangement, very easy. And if you know Wolff rearrangement, Hoffman degradation is also very easy. No need to remember, directly you can attempt the questions. N-bromamide, otherwise you can say N-haloamide. Amide anion, this is called amide anion. These two are intermediates in this reaction. Okay. So one more intermediate is there, nitrine is also one more intermediate. But nitrine is unable to trap, like an oxygen. So can you trap oxygen? No. But without oxygen we won't live. Here also same. But we know definitely oxygen is there. But we are trapping the oxygen, but it is impossible to trap. But we are converting like this. So here also nitrines are intermediate. That nitrines have a tendency to give this product, but it is unable to trap. Amide, amide anion, haloamide, N-halo, amide anion, isocyanate, this is isocyanate, carbamate, this is carbamate, and finally amine, primary amine. It will come one more time in rearrangements, clearly I will explain with more number of applications and stereochemistry regarding the rearrangement. There you learn clearly. Right now our target is where nitrines are involved in rearrangement reactions. It is involved in half-main rearrangement in the form of acyl nitrine. Clear? Now here you write one point. Intermediate in this reaction is, what is intermediate? Intermediate in this reaction is, see here, acyl nitrine, N-halo, amide anion, next here followed by N-halo amide. Okay, N-halo amide. You remember this point, acyl nitrine. So is it acyl nitrines are isolated? Is it possible to trap or not? I am saying, see, acyl nitrines are unable to trap, unable to detect or unable to isolate. Isolate nothing but identification. Unable to isolate or detect. What is the reason? Due to its instability. Already nitrine is unstable, acyl group is withdrawing that particular nitrogen electrons. Finally acyl nitrine is unable to trap. Okay, acyl nitrines are unable to isolate due to its instability. Intermediate is nitrine but not possible to identify. That's what I am saying. So whatever stereochemical aspects are there, applications are there, that we will see individually. After completion of nitrine, next most nitrine to benzene, later I will start molecular rearrangement. In that one you will see these all reactions, how intermediates are helps in molecular rearrangement. Clear? Now go second rearrangement. This is very, very important and most expected in your examination, courteous rearrangement. Courteous rearrangement. Courteous. What is courteous rearrangement? See, RC double bond O, nitrogen carry triple bond with other nitrogen and negative charge with this. This is called acyl azide. Remember, Acyl azide involved in Curtius rearrangement. Curtius rearrangement is thermal or photochemical reaction which is usually convert acyl azide to, acyl azide is get converted to isocyanate, N C double bond O like this. Curtius rearrangement is conversion of acyl azide to isocyanate. Okay. In this one what happens, see, initially loss of N2 takes place. When loss of N2 takes place, what you observe? There is a formation of a acyl nitrine, right? There is a formation of acyl nitrine. Then this lone pair migrate here, this R migrate here. Finally, what is the answer? This is the one. But this nitrine is not trapped here. Okay, it is a simultaneous process. Loss of N2, migration of R will take place simultaneously. So when this kind of reactions are observed, remember, on one molecule if they are given multiple arrows, definitely it may be a carbon or nitrine. Multiple times if they write on nitrogen, see, nitrogen electrons are going, group is going and one group is coming. When any atom, if one group is going and one group is accepting and electrons are mobiling, definitely it is an electron deficient species. This is a nitrine intermediate. So same thing if it is happens on carbon, carbon intermediate. Remember, group is going on, one group is coming and negative charge or any electrons are mobiling, then definitely it becomes a either carbon intermediate or nitrine intermediate. Be careful with this kind of arrows. See, on one atom how many operations are observed? One group is going from same atom and one group is coming on that atom and electrons also mobiling. And be careful with this one. It is giving a unstable nitrine, it is impossible to trap and finally you will get expect a rearrangement product of isocyanate, not isocyanide. Isocyanate, name is very important. If I write sulfur, here if I write sulfur, sulfonylamine. If I write carbon, ketene. Where we learn ketene? Wolff rearrangement, untested rearrangement. Like that we need to compare. Remember, when you learn untested rearrangement, three reactions will be in your hand. Wolff rearrangement, Hofmann rearrangement, and one more is untested original reaction with a carbon intermediate as well as nitrine intermediate. Okay, right. Curtius. Try to deliver names clearly without any mistakes. Acyl azide. If I write alkyl group here in place of this, if I write alkyl, alkyl azide. If I write hydrogen, hydrozoic acid. Clear? Now, so this is called Lawson rearrangement. Next is Lawson. Lawson rearrangement is carried out under thermal, acidic medium as well as basic medium. Here what we are using? Here we are using hydroxamic acid derivative. Hydroxamic acid or its O-acyl. Acyl I am taking. See, this is nitrogen with O C double bond O R. So otherwise we can use R C double bond O. It is attaches to nitrogen and see this is attaches to O aryl C double bond O A R. O aryl acyl like that we can take any one. Okay. Now this carbon is attaches to oxygen and here it may be hydrogen or it may be acyl or aryl, benzoyl. Okay, benzoyl derivative like that we can take any one of this. Any one of this if you take. Now this is on treatment with a basic medium or acidic medium, otherwise thermal or photochemical, everything is possible. So finally what happens, see, remove this alkyl, put on this nitrogen and finally what is the answer? You may get NH2. So this I will show in the form of acidic medium C. when proton is added here and when base is given, base will take proton here. So all mechanisms are not required, directly one mechanism I am showing. Suppose if I take a base, base will take proton from here. Suppose if I add acid, acid will be added here and there is a loss of water molecule. Okay? So when water molecule is removed, this R will migrate here. Suppose if base is added, now negative charge will be appeared here. Suppose if negative charge is appeared on nitrogen, what is present already? OH. Now this negative charge migrate here, R will migrate and OH is migrate. See, on one nitrogen, one group is going on, one group is coming around nitrogen and electrons are mobiling opposite side. Then finally what is the answer? Answer is NC double bond O, isocyanate. Isocyanate on treatment with water. Isocyanate on treatment with water gives amine. This is called Lawson rearrangement. So what is the name of this acid? Hydroxamic acid. You remember this one. Hydroxamic acid and their O-acyl derivative. O-aryl. This is O-aryl and what about this? Aroyl. This is not A-R-Y-L, aroyl, A-R-O-Y-L. And this is hydroxamic acid O-acyl. This is O-acyl and this is called O-aroyl. Hydroxamic acid O-aroyl. Hydroxamic acid O-acyl. If they treat with thermal, acidic and basic medium, that may give isocyanate. That isocyanate on treatment with water, that will give primary amine. So this is called Lawson rearrangement. Every rearrangement name is very important. What is intermediate, what is final answer? Okay, hydroxamic acid O-acyl, hydroxamic acid O-aroyl. Don't say aryl. If you write the word aryl, it is wrong. Aryl is different. Aryl means benzene. So this is last one in rearrangement. Smith rearrangement. This is called Smith rearrangement. Smith, S-C-H-M-I-D-T, Smith rearrangement. Smith rearrangement. So what is Smith rearrangement? See, I am taking a alkyl group attaches to C double bond OH. Is it a carboxylic acid? Carboxylic acid on treatment with, what is this? HN3 in presence of H2SO4. Hydrozoic acid in sulfuric acid. First what happens, see, this H2SO4 will donate one proton to organic acid. So when this acid donates proton to carboxylic acid is going to be acts as a base. Okay, after acting as a base, they will lose water molecule and there is a formation of a, what is this? Acyl cation. So can I write carbon-carbon double bond or not? This is stabilized by these non-bonding electrons like this. After stabilizing, can I write directly? So what you will expect? R, C, triple bond O, can I write positive charge on oxygen or not? Now you will get acyl cation. This acyl cation is going to react with this molecule. See, try to identify this. Nitrogen carry negative and here hydrogen. What is this? This hydrozoic acid only. Okay. Now this hydrozoic acid attacks on this carbon and these electrons migrate to oxygen. And finally C, can I write C double bond O nitrogen which carry nitrogen triple bond and this is plus and what is this? Hydrogen. Suppose if I remove this proton, if I put negative charge, what is that? If I remove this proton and if I put a negative charge here like this, acyl azide, where we observe this molecule, where we observe this one, cut TS. So if I put a hydrogen here, this is called protonated acyl azide. Protonated acyl azide. Now what happens, see, in this case this lone pair will migrate here and this will migrate over here and N2 will be removed. Now negative charge is not migrating, lone pair is migrating. So on that time what is removed? N2. See, one group is going on, one group is enter on nitrogen, electrons are moving opposite side to nitrogen. And finally can I write like this, R is retains their orientation on nitrogen. Nitrogen carbon double bond, carbon oxygen double bond. And what about charge present on this one? Positive. This is called protonated isocyanate. These two are important in case of Smith rearrangement. In normal cases you will get a acyl azide, now you will get protonated acyl azide. In normal cases you will get isocyanate, in this case protonated isocyanate. This point is important. It is appeared only in Smith. Protonated isocyanates are isolated in Smith rearrangement, but it is not isolated in case of Hoffman, it is not isolated in Curtius and Lawson even. But intermediate is nitrine only, nitrine intermediates only. And see, later on this proton will be removed here. After removing this proton, it is readily forms carbon nitrogen double bond. What is this? Isocyanate. Then later on treatment with water. Can I write direct answer? Now, what is the final answer? R is attaches to NH2 and there is a loss of carbon dioxide. So finally what we prepared? Amine. So can I break this total bond here? Can I remove this total? Remove this total, remove carboxylic acid and place a NH2 group. Remove this group, put NH2. Right or not? If carboxylic acid is replaced by amine group, that rearrangement is called Smith rearrangement. And what are the starting materials required in Smith rearrangement? Hydrozoic acid and H2SO4. Conversion of carboxylic acid to amines in presence of hydrozoic acid and H2SO4 is called Smith rearrangement. Every rearrangement and name reaction, try to remember what are the reactants used in that one and what are the reagents and what are the intermediates and what is the stereochemistry. They are sufficient. You can attempt definitely one question. This is called acyl cation, protonated carboxylic acid. Already it is protonated. Acyl cation, resonance form, hydrozoic acid, protonated acyl azide, protonated acyl azide, protonated isocyanate, isocyanate amine. So take one question. Now, which of the following rearrangement produce nitrine as a intermediate? Nitrine as an intermediate. In which rearrangement reaction nitrine is a intermediate? Okay. Wolff rearrangement, option B. Beckmann rearrangement, next C. Stevens rearrangement, option D, none. In which rearrangement nitrine is an intermediate? Say the answer. So right now whatever rearrangements which you learn, in that one no one of the option is given, right or not, so that you can predict very easily, but I not given. So answer is none or Beckmann? No, none only. Beckmann is a nitrogen rearrangement, but it is not a nitrine rearrangement. Oximes converted to amide. Oxime to amide is a Beckmann, but it is not a nitrine rearrangement, it is a nitrogen rearrangement. Nitrine rearrangements are only Hoffman, Curtius, Lawson, Smith. Clear? Next. Which of the following is not a nitrine rearrangement? Which of the following is not a nitrine rearrangement? Hoffman, Lawson, Curtius, then Beckmann. Which is not a nitrine rearrangement? That is Beckmann. Sometimes these letters they will give some selective words, they will give and they will ask. Which is not clearly, they will highlight and they will ask question. Identify the reaction. So here I am giving CONH2. Now I am giving NaOBr. Now I am giving RNH2. Option A. Hoffman rearrangement, Curtius rearrangement, Lawson rearrangement, option D, none. Bromine in sodium hydroxide if I given, then you can give the answer, right? But still it is Hoffman only. Bromine in sodium hydroxide will give NaOBr. What is sodium NaOBr? Sodium hypobromite, hypochlorites. Bromine in sodium hydroxide will give this intermediate. So even this combination also give Hoffman. The product involved in following reaction is. The product involved in following reaction is. So what is the product you will expect in this reaction? The product involved in this reaction is option A. This is CSR question, but intermediates they given two, they given A and B, but straightforwardly I changed the question and I am giving. Almost all same question, but slightly I changed. I am not asking intermediate, directly I am asking the product. They asked two, NARISH 1, NARISH 2, like that also they given. Why? Because photochemically given or not. They will ask NARISH 1, NARISH 2, pattern of Buch reaction, PB, Barton reaction, etc. Now what is the answer? Silicon, what is this molecule? C. Here I am giving C double bond, and what I given? Nitrogen double bond, nitrogen. Can I put negative here? And this is positive. If this negative charge migrate here, it will transfer on this carbon. Now what is the resonating structure you will expect? Is that carbon carry negative charge? Now nitrogen carry triple bond, here positive and this is negative. Clear? Now after this, this bond will migrate here and this will attack here and this will remove out. So what is your answer? So initially see, here you may get a bond like this. Now this carbon connected to this one or not? This carbon initially bonded here, now it is connected to this one. Now here what will get? Double bond. Here will get double bond. Later on this and this carry C double bond go like this. What is this? Ketene. Which rearrangement I given? Wolff rearrangement. I given Wolff rearrangement. Okay, I am not given untested rearrangement. It is a Wolff rearrangement product. What is Wolff rearrangement product? Ketene. Can I stop here? Can I add water molecule? If you add water molecule, that is untested. If you restrict reaction up to here, that is Wolff rearrangement. They given only photochemical symbol. So they given only photochemical, which means don't add water molecule. Try to restrict reaction up to diazoketone to ketene. So your answer is C. So what is intermediate in this one? Carbene. This is intermediate, but this is not final answer. Intermediate is carbene, but what he was asking? Final answer he was asking. Proceeds with acyl carbene, but acyl carbene is not intermediate, it is not trapped clearly. So final answer is what? What is final answer? Ketene. Ketene is the final answer. It will comes one more time in rearrangement reactions clearly. There I will explain many applications, but right now remember intermediate in every reaction. Okay, untested rearrangement proceeds with a Wolff rearrangement. Wolff rearrangement proceeds with a carbene intermediate. Nitrine intermediates are Hoffman, Curtius, Lawson as well as Smith. Beckmann is not a nitrine intermediate, it is proceeds with a nitrogen intermediate. Initially we are using a oxime. Oxime is converted to amide, that is called Beckmann. So that is end of nitrines. So 5 intermediates we discussed, starting from carbocation, then followed by carbanion, then we learn free radical, then carbene as well as nitrine. So complete structure, generation, then followed by trapping methods, stability and chemical reactions. So what are the chemical reactions? You will observe regarding carbocation, addition and elimination. Carbanion. Carbanion means condensation, substitution, elimination, chain lengthening and some rearrangements. Okay, free radical. Free radical. Thermal reactions, photochemical reactions, redox reactions, okay, auto-oxidation, then followed by disproportionation reactions also possible, okay, anodic oxidation, cathodic reduction, base catalyzed reactions also expected. Carbene, carbenes undergo which reactions? Cycloaddition, insertion, then cyclation, that is cyclopropanation reactions, finally you can go for rearrangements. Nitrine reactions, same, cyclopropanation or cycloaddition reactions, insertion reaction, dimerization reaction, disproportionation reaction, finally a rearrangement reaction. Rearrangement reactions are very important for nitrine. So some rearrangement reactions are Hoffman, Cutier's, Lawson and Smith rearrangements. Okay, so that is end of nitrines. Tomorrow we will discuss benzene. Benzene is there. So even though benzene is not given directly in your syllabus, especially JL syllabus I am saying, it is not given directly in your syllabus, but definitely they will ask in pericycle. Now benzene which helps in pericyclic, that intermediate we are discussing in react intermediates only. Okay, we will stop here, we will continue next class.